we've been talking about gas laws. We talked about some of the simple gas laws. Now we're going to talk about what's called the ideal gas law. So this is actually, in a way, a combination of the simple gas laws. You can put them all together and end up with the ideal gas law. So we saw the relationships. Volume is proportional to 1 over pressure. Volume is proportional to the temperature of a gas, and the volume is proportional to the number of moles of a gas. So if you combine those, you get volume being proportional to NT over P. So if those are proportional, that means that one equals a constant times the other, a proportionality constant. So we get this, and that can be, R is the constant, and we can rearrange that into PV equals nRT. That is the ideal gas law. So let's put a box around that. This is the ideal gas law, sometimes called PIVNERT. You know, it's like, well, if you tried to pronounce that, how would you pronounce it? PIVNERT, right? R is the ideal gas constant. A constant is constant. It doesn't change, right? But the value of it will depend on what units you use for the pressure and the volume. The temperature is always in Kelvin. The amount of gas is always in moles. But the pressure and the volume can be measured in different units. So mostly we use atmospheres for pressure and liters for volume. And when we do that, R is equal to 0.08206 liter atmospheres per mole Kelvin. So that's the ideal gas constant. This is a good thing to memorize because we're going to use it a lot. It'll save you a lot of time. The units are messy looking, but they're important and they're useful. So if we take this equation and rearrange it for R would equal PV over NT. The units for volume are liters. The units for pressure is atmospheres. The unit for N is moles, and the unit for T is Kelvin. The units on the ideal gas constant tell us what the units on the other quantities should be. So always include the units, make sure they're canceling out correctly. Any questions yet? This is a slide that just shows how you can get Boyle's law, Charles' law, and Avogadro's law from the ideal gas law. So Boyle's law that volume is proportional to the inverse of pressure. Volume is proportional to temperature. Volume is proportional to amount of moles, amount of gas in moles. I want to show you one other way to get not just those proportionalities, but the actual equations that you need. No, that's not what I wanted. I want this one. Oh, that's weird. This one? Yeah, that's better. So if you remember PV equals nRT, that's actually the only gas law that you have to remember. The other gas laws have, like one of them is P1V1 equals P2V2, and some of them have fractions in them, and they get really confusing. So let's do this. PV equals nRT. Divide that by PV equals nRT. If PV equals nRT, then if we divide this by something that's the same on each side, it's still an equality, right? So some of you are going to follow this derivation. That's awesome. Some of you are not going to follow the derivation. It's still a simple enough concept that you don't actually have to understand what I'm doing. So let's put subscripts of 1 on those in the top and subscripts of 2 on the bottom. I'm taking one ideal gas law and dividing it by another ideal gas law. I did not put any subscript on R because R is a constant. It doesn't change. So here we have this big old mess. This contains all of the simple gas laws and another one called the combined gas law. So what we're going to do here is we're going to cancel out anything that doesn't change in our problem. So R is never going to change, so I'm just going to erase that. So we can get rid of R. So the first law we learned was Boyle's law, and in Boyle's law, the amount of gas and the temperature are the same. So what would happen if N1 and N2 are the same number? They cancel out, right? So those cancel out. And if the temperature doesn't change, T1 and T2 are the same. All that canceled out. So what is this right side equal to? 1. Okay, so now we've got P1V1 over P2V2 equals 1. Well, if we multiply both sides by P2V2, we get P1V1 equals P2V2. It's magic. It's math. Yes, it is. And math is magic. You can do that for any combination. Okay, so you can memorize the gas laws. If you're good at memorizing, that might be the easiest thing. I like to have a way of thinking it out so I don't have to keep all these details in my head. Or you can do this. And just look at the problem that you're dealing with. Whatever is not changing, you cross those out. And then you don't have to put it in this form before you rearrange it again. You can take it from here and say, well, I need to solve for P1 and rearrange it as needed. Okay? So there's a technique for remembering the gas laws. Any questions? Okay, let's do some practice with the ideal gas law. An 8.50 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres and PSI of the gas in the tire? So this is an ideal gas law problem because it says ideal gas law up here, right? What if this is on an exam and we don't recognize that? As you read through the question, you may notice there's only one volume. There's only 1 moles. There's only 1 temperature. We're not talking about things changing, expanding, heating, cooling, nothing like that. So that gives you a clue that we don't need one of the simple gas laws. The other thing you can do is it's like, well, I don't know what gas law I need. I'm just going to make the table. She said make a table. I'm going to make a table. So let's see what happens if we just make a table. So 1 and 2. Go through the problem, write down the numbers. So here are 8.50 liters. Well, that's volume, right? It doesn't say volume, but liter is a unit of volume. You should know that. 0.552 moles. Well, what letter do we use for amount of gas in moles? N. At a temperature. So these 3 numbers are all going together. So, okay, we need to extend our table. 305 Kelvin. Well, that's nice. They put the temperature in Kelvin so we didn't have to convert it. So that's the temperature. We ran out of numbers. Those are all the numbers. There is no second row. Is the table worthless? No, you just identified V, N, and T. So you've got everything labeled so you could use the ideal gas law. So if you make a table and you end up with 1 row, it's going to be the ideal gas law. If you make a table and you end up with 2 rows where you've got things changing, then you're going to need to use one of the other gas laws. So I'm just going to get rid of this extra row that we don't need, because for some reason I find erasing things on here to be strangely satisfying. It's weird, I know. I'm very weird. Ask anybody. Okay, so we need the ideal gas law. PV equals nRT. PV equals nRT. What are we trying to find? The pressure. So we need to take this equation, rearrange it, solve for P. So I want to get rid of V, so I'm going to put V on, divide by V on both sides, right? So now I've got P is equal to nRT over V. What's R? The ideal gas constant. R equals 0.08206 liters atmospheres over mole kelvins. These are the units that I need on my other quantities. Are they matching up? I've got liters and moles and Kelvin. Yeah, that's good. So I don't need to do any unit conversions. So I'm just going to start plugging things into my equation. So N is 0.552 moles. And R, this big old mass, 0.08206 liters atmospheres per mole Kelvin. And the temperature is 305 Kelvin. And all of that divided by the volume, 8.50 liters. When we check out the units here, we see that they cancel nicely. The liters cancel, the moles cancel, the kelvins cancel, and I'm left with a unit of atmospheres, which conveniently is a unit of pressure. So in terms of showing your work, this line right here, this is what I want for showing your work. You don't have to show this, you don't have to show that, but I do want the rearranged equation written down, and then I want all the numbers with their units plugged into it before you write out the answer. Because then if something goes wrong, I can help you figure out what it was so that you can avoid doing that again. Because what's the point of making mistakes if you don't learn from them? So 0.552 times 0.08206 times 305 divided by 8.5 equals. How many significant figures should this answer have? 3. So all of the values that we were given have 3 significant figures. The ideal gas constant, this is not exact, but this has 4 significant figures. So I'm coming up with 1.62. There's my 3 sig figs. The next 2 digits are 5 and 3. The unit is atmospheres. So it asks for the pressure in atmospheres and PSI. So in atmospheres, it's 1.63 atmospheres. That's one answer. It asks for 2 answers. So then what do we do? How do we get PSI? I'm going to convert it, right? So we'll take this. I'm going to use the unrounded version, and I'm going to convert to PSI. So PSI on top, ATMs on the bottom. So you would look this up. I wouldn't expect you to remember this. And I'm going to give you the 4-digit conversion on an exam. It's 14.69, not 14.7. PSI per atmosphere. This will also have 3 sig figs then, 23.876. So we'll round that to 23.9 pounds per square inch PSI. Any questions? This is like the most straightforward ideal gas law problem you could have, really. Yes?
Would you want us to memorize the number for R?
You should memorize the number for R. It may be given, but I wouldn't count on it, and you're going to use it so much, you'll probably memorize it by accident if you do all the homework. Let's do another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? So we could make a table. As we read through this, we could also recognize nothing's changing. I've just got one N, I've got one P, I've got one T. They're asking me for V. This is going to be an ideal gas law problem. So I'm still going to take these numbers out and identify what they are, but I'm not necessarily going to make a table. You can, but I'm not going to this time. So I've got 0.556 moles. Well, we use lowercase n as the symbol for amount of gas in moles. So that's N. I've got pressure of 715 millimeters of mercury. So that's P. And the temperature is 58 degrees Celsius. They're asking me for V. Okay. So PV equals nRT. Rearranging that, I get V equals nRT over P. Before we plug these numbers into the equation, let's make sure the units are okay. Is millimeters of mercury going to work with the ideal gas constant? No. It needs to be in atmospheres. So I need to convert that. So millimeters of mercury on the bottom, atmospheres on the top. Pressure conversions are always one step. This is one you should remember. 1 atmosphere is 760 millimeters of mercury. That conversion is exact. So I've got 715 divided by 760. So that's 0.94078 atmospheres. I am going to use this number in the calculation. I want to carry 2 extra digits. Okay? Temperature, 58 degrees Celsius. Is that going to work? No. So let's convert that to Kelvin by adding 273. If you want to do the 273.15, I'm all for that. But like I said, I'm feeling lazy this semester. That's going to give us 331 Kelvin. The way I'm going to treat that number this semester is I'm going to look at the temperature. Here, this is given to me to the nearest ones place. So then I feel okay just adding 273. If it was given to 1 or 2 decimal places, I would definitely want to use the 0.15. That's not going to make or break your answer here. Okay, so we got moles, atmospheres, and kelvins, and we can plug those into our equation. So 556. The 2 was the last one. Then we've got R, 0.8206 liter atmospheres per mole Kelvin. It's a constant. It's always the same. You know what it is because you memorize it. And the temperature, 331 Kelvin. I'm going to divide by pressure. 0.94078 atmospheres. Double check the units. Understanding units really can help you a lot. If you know the units on the ideal gas constant, you could actually figure out what the ideal gas law is just by putting things together so the units cancel out. That's how my high school physics teacher taught us that we could fake our way through physics. So those units cancel out. I get a volume unit of liters, so that's a good sign. 0.556 times 0.08206 times 331 divided by 0.94078 equals. I look at all those numbers. I've got 3 significant figures. So 16.0, there's my 3 sig figs. Write down 2 extra digits. The unit is liters. Now round it, 16.1 liters. Any questions? So this one's fairly straightforward, but requires unit conversions on the pressure and the temperature.